So, welcome to module 20. In this module, we will discuss properties of distribution function of a random vector. We have already discussed the properties of distribution function of a random variable. So, here we will discuss the properties of distribution function of a random vector. So, suppose I am given a random vector x, which is a p-dimensional random vector, and this is defined on a probability space omega p omega p. Suppose this has distribution function f x. So, f x x is nothing but probability x less than or equal to x, which is same as p x minus infinity to x. So, which is basically probability of all those omega belonging to omega, such that x omega is less than or equal to x, and this is defined for various x in R P. Now, this p x is the probability function induced by random variable x. Now, we have seen that if one has to get the probability that x belongs to a p-dimensional rectangle A B, one can get this probability through distribution function using this relation. So, summation k is equal to 0 to p minus 1 to power k, z belonging to delta k p A B. So, delta k p A B is the set of all those vertices of the p-dimensional rectangle A B, such that k of them are ai's, and I know that ith component has to be ai or bi times f x it. So, now let us study various properties of a distribution function. Now, let x equal to x1 x2 be a p-dimensional random variable with distribution function f x. Then, if I take all of the arguments to plus infinity in the distribution function, I get value 1. So, here I can use the iterated limit. So, that means I can take first x p going to infinity, then x p minus 1 going to infinity, and then x 1 going to infinity. And I can do it in any order. I can take first x 1 going to infinity, then x 2 going to infinity, and x p minus going to infinity. Now, these iterated limit would exist and would be same as the limit. One can prove that using advanced arguments from calculus, which I will not do over here, but in this case iterated limits would exist and they would be same as the exact limit. Now, similar thing happened for p is equal to 1. That means limit x going to infinity f x x is equal to 1, that we saw. Now, for each I belonging to 1 p, so that means if I take any of the argument to minus infinity in the joint distribution function, then I get the value 0. So, in the case of p is equal to 1, for example, we saw that limit x going to infinity f x x is 1, then limit x going to minus infinity f x x is 0. So, these are analogues of those two properties. We also saw in the p is equal to 1 case f x x is right continuous, which is here f x x 1 x 2 x p is right continuous in each argument when other arguments are kept fixed. So, these three properties are analogous properties for the case p is equal to 1. Now, in the p is equal to 1, what we saw is f x is non-decreasing. Its analog in p dimension is that for each rectangle A B belonging to R P, this is positive, greater than or equal to 0. We know that this is same as probability that x belonging to a rectangle A B is greater than or equal to 0, which is always true because probability is always greater than or equal to 0. So, what we have is a distribution function satisfies these properties. So, let us try to prove them. The idea of the proof is the same as the one in the case of p is equal to 1. So, let us consider the first part where I have to consider the iterated limit m going to infinity, n going to infinity, f x 1 x 2 m n. So, this is same as limit m going to infinity, limit n going to infinity, f x 1 x 2 m n is same as probability x 1 less than or equal to m, x 2 less than or equal to m. Now, note that in this case this is an increasing sequence in n, because to begin with m is fixed, so x 1 less than or equal to m, x 2 less than or equal to 1, x 1 less than or equal to m, x 2 less than or equal to 2. So, as n is increasing, this set is increasing, and since it is a limit, I can take it inside and convert the limit into union. So, with equals becomes union n is equal to 1 to infinity, x 1 less than or equal to m, x 2 less than. If I consider a union of x 1 less than or equal to m, x 2 less than or equal to n, what is happening? I can go as much nearer to infinity as I wish. Not a very precise statement, but what I am saying is I can make this n as large as I wish by taking enough number of unions. So, in a sense, this will be same as limit m going to infinity, probability x 1 less than or equal to m and x 2 less than infinity. But probability x2 less than infinity is 1. So, this is same as this probability is same as probability x1 less than equal to m, which is same as limit m going to infinity f x1 m, and that we know is same as 1. One could have directly done it over here, because when I take the unwanted variable to infinity, I get the marginal of x1. So, I could have written this as directly over. There was no need to go through all these arguments, because we have seen that if I take the unwanted variable going to infinity, I get the marginal. So, here if I consider this quantity, so here unwanted variable is the 1 x2, its argument is going to infinity. So, I should get a marginal of x1 at point m, so which is x1 going to m, and this is 1. So, there was no need to do all this, but to make things clear, I have repeated those steps over here. Now, I have to take one of the arguments going to minus infinity, and then so that f x1 x2 is 0. So, let us consider x1 going to minus infinity f x1 x2. Now, since this limit exists, this is same as limit m going to infinity f x1 x2 minus m x2, which is same as limit m going to infinity probability x1 less than or equal to minus m, x2 less than or equal to x2. Now, as m is going to infinity, this is a decreasing sequence, x1 less than or equal to minus 1, x1 less than or equal to minus 2, and so on. So, this is a decreasing sequence. This is decreasing in m, as m increases, decreases. So, this is a limit. So, that is why when I take it inside limit, it becomes an intersection, probability intersection m is equal to 1 to infinity, x1 less than or equal to minus m, x2 less than or equal to x2 by continuity of probability functions. Let us see what is this intersection. Now, to begin with, x1 less than or equal to minus 1, then x1 less than or equal to minus 2, x1 less than or equal to minus 3. So, I can make this minus m as small as I wish. So, finally, I can exclude any point I want by taking m large enough, because x1 less than or equal to minus m, and minus m could be very small quantity. So, that is why this intersection will be nothing but phi. So, this same as p of phi, which is nothing but 0. Now, similarly, one can show that if x2 going to minus infinity, then f x1 x2 is also 0. Now, let us see the right continuity. The idea of proof is similar to the case of p is equal to 1. So, for x1 x2 belonging to R2, let us consider limit n going to infinity f x1 x2 x1 plus n x2. So, I am seeing the right continuity in the first argument over here. So, this is same as limit n going to infinity probability x1 less than or equal to x1 plus n, x2 less than or equal to x2. N is equal to 1, this is x1 less than or equal to x1 plus 1, n is equal to 2, x1 less than or equal to x1 plus half. So, x1 plus 1 is over here, x1 plus half is over here, and keep on. So, this is decreasing, this is fixed. So, as a joint event, this is a decreasing sequence of events. Limit is outside. So, by continuity of probability function, when I take the limit inside, it becomes intersection. So, intersection n is equal to 1 to infinity, x1 less than or equal to x1 plus 1, x2 less than or equal to x2 plus 1. Note that x1 is over here, and I am moving from the right. So, when I am taking the intersection, finally, it will become x1 less than or equal to x1, x2 less than or equal to x2, which is same as f x1 x2, x1 x2. So, this clearly implies that f x1 x2 is right continuous in first argument. So, you see, when I keep x2 fixed, I approach x1 from the right, this is same as f x1 x2, x1 x2. Similarly, it can be shown that f x1 x2 is right continuous in the second argument. Let us try to prove the fourth property. So, let minus infinity less than a1 less than b1 less than infinity, and minus infinity less than a2 less than b2 less than infinity. Let us consider this quantity. So, first k is equal to 0, minus 1 to power 0 is 1, z belonging to delta 0 2. So, that means none of them is a, both of them are b. So, f x, the first coordinate always has to be b1 or a1. So, b1 and b2. Then k is equal to 1, all those will come with a minus sign, and k is equal to 1, that means only one of them is a. So, a can be in the first coordinate or the second coordinate. First coordinate it has to be a1, so a1 b2. Second coordinate it has to be a2. These come with a minus sign. Then k is equal to 2, minus 1 to power 2 is a positive factor, and then both of them are a's. So, that is for f x a1 a2, and one can easily see this. We have seen before, this is same as probability x1 greater than a1 less than or equal to b1, x2 greater than b2 less than or equal to b2, which is always greater than or equal to 0. So, you get these four properties. So, any distribution function will satisfy these 4 properties. Now, let us see what happens the monotonicity in each argument when other arguments are kept fixed. So, let f x be the distribution function of p dimensional random vector for h greater than 0 and a1, a2, ap belong to RP. Let us consider f x a1 plus h, a2 to ap, a1, a2 to ap. So, I am seeing here whether it is increasing in the first coordinate when other coordinates are kept fixed or not. So, this same as probability x1 less than or equal to a1 plus h and xi less than or equal to ai for I is equal to 2 to p minus probability x1 less than or equal to a1 and xi less than or equal to I is equal to 2 to p. So, here in this is fixed. So, this is same as x1 less than or equal to a1 plus h minus x1 less than or equal to a1. So, if you do this, use the additive property of a probability function, this becomes probability x1 greater than a1 less than or equal to a1 plus h, and these are fixed anyway, xi less than or equal to I is equal to 2. But probability is always greater than or equal to 0. So, this is always greater than or equal to 0. So, it follows that the distribution function of a random vector is non decreasing in each argument when other arguments are kept fixed. Now, note that for p is equal to 1, the fourth condition in p is equal to 1 was that f x is non decreasing. The fourth condition over here is that this is greater than or equal to 0 with p over here. So, how the two things are equivalent in the case of p is equal to 1? Let us try to see. For p is equal to 1, condition D of the above theorem is equivalent to saying that probability that x belongs to a p dimensional rectangle A to B is greater than or equal to 0. So, which is same as probability that x lies to one dimensional rectangle which is an semi closed interval A to B is greater than or equal to 0. So, the D condition which we wrote down in last but one slide is equivalent to this, but this is equivalent to saying that what is this quantity? This is nothing but f x b minus f x a is greater than or equal to 0, which is equivalent to saying that f x b is greater than or equal to f x a whenever a is less than b, which is equivalent to saying that f x is non decreasing. So, in the case p is equal to 1, f x is non decreasing is equivalent to saying that probability that x greater than a less than or equal to b is 1. In the case of p dimensional, for p dimensions, this condition translates to saying that x belongs to a p dimensional rectangle A to B is positive, which is in terms of distribution function written in the form summation k is equal to 0 to p minus 1 to power k summation z belonging to delta k p f x z is greater than or equal to 0. Now, what we have seen is any distribution function satisfies those four properties. Now, one can show that if a function g satisfies properties mentioned in A to D of above result, then there exists a probability space omega p and a random vector x equal to x1, x2, xp on omega such that g is the distribution function of x. So, that means any function which satisfies these four properties A to D is a distribution function of some random vector. Now, clearly the distribution function f x x is determined by the induced probability space p x. Now, conversely it can be shown that if you know the distribution function f x, then you can know this induced probability function p x. This suggests that to study the induced probability function p x, it suffices to study the distribution function f x, and that is the reason why we concentrate on distribution function, which is easier to study in relation to the induced probability function, and we forget about the induced probability function. So, that is the reason why distribution function is so important. One can restrict only to the distribution function, and from there one can get all the information about the induced probability function. Now, let me give this as a take home problem. So, let f from R2 to R be given by this. So, this is a function. Does f defines a distribution function of some random vector? So, you have to see whether this satisfies those four properties or not. So, take this as an exercise. Now, before I end, let me give a brief summary of the things I will be doing in the next module. We will introduce the notion of discrete random vectors and discuss their properties. So, the way we introduce the concept of discrete random variables in one dimension, now we will introduce the notion of discrete random vectors and we will discuss their properties. So, that was all for this module. Thank you for your patience and have a great day.